Wanted to work through an example involving RC circuits, specifically about the time constants of RC circuits. As you know, when you charge up a capacitor through a resistor, that takes some time. There's a characteristic time constant. As you discharge a capacitor through a resistor, that takes some time. There's a time constant. And so this question is all about evaluating time constants for different circuits involving resistors and capacitors. I've got three circuits here. The one on the left is a very simple circuit. It's just a single resistor and capacitor. We're going to write down the time constant for that. It's kind of a reference point. Then the second two circuits involve either a parallel arrangement of identical resistors and a series arrangement of capacitors, or a series arrangements of identical resistors and a parallel arrangement of capacitors. And we're going to figure out the time constants of these two other circuits. So this brings together our understanding of time constants, discharging, charging capacitors, also brings together our understanding of resistor circuits, capacitor circuits, resistors in parallel and series, capacitors in parallel and series. So let's go ahead and do this. The first example over here on the left, well, this is the simplest RC circuit, resistor capacitor circuit. The time constant of the resistor and capacitor in series, that is the timescale for charging this capacitor up through this resistor or discharging this capacitor through this resistor, is just the product of the resistance of the capacitance. So let me just write that down. Tau, the symbol we use for the time constant, is just going to be RC. So the bigger the product of R and C is, product of resistance and capacitance, the longer the time constant, the longer the time to charge up or discharge this capacitor in this circuit. Let's now move to the two other circuits, start in the middle and then we'll work to the right. What's the time constant for these circuits? Well, the starting point is that the time constant for this circuit here is the product of the equivalent resistance of this circuit and equivalent capacitance of this circuit. So there's two resistors in the circuit. They will form some sort of equivalent resistance. And there's a couple of capacitors in the circuit that will form some sort of equivalent capacitance. And it's the product of those two equivalent quantities, equivalent resistance, equivalent capacitance, that will determine the time constant. So we just got to work those out. Now, this is a fairly straightforward problem because we've just got pairs of components either in series and parallel. And actually, in this case, the components, like the two resistors, are identical resistors. The two capacitors are identical capacitors. So let's just go through this quickly. For the two resistors, in parallel, we're going to make a smaller resistance. And the specific rule for combining resistors in parallel is that the reciprocal of the equivalent resistance is equal to the sum of the reciprocals of the individual resistances. So we have two resistors, resistances R and R. Their reciprocals are 1 over R, 1 over R. The sum of their reciprocals is going to be 1 over R plus 1 over R is 2 over R. That's the reciprocal of the equivalent resistance. So the equivalent resistance itself is actually R over 2. We've just made a smaller resistance with our resistors in parallel. And because they were equal resistors, is half the value of the individual resistances. So that's simple. What about the capacitors? For two capacitors in series, we make a smaller capacitance. It's harder to store the charge on this arrangement of capacitors. The rule for combining two capacitors in series is actually resembles the rule for combining two resistors in parallel, is that the equivalent capacitance is the the inverse of the equivalent capacitance is the sum of the inverses of the individual capacitors. So in this case, again, we're lucky we got two identical capacitors. The inverse of the sum of the inverses of the capacitances is 1 over C plus 1 over C. 1 over C plus 1 over C is going to give us 2 over C. That's the inverse of the equivalent capacitance. So the equivalent capacitance itself is going to be C over 2. So again, we made a smaller capacitance, kind of like we made a smaller resistance here. Well, at this point, we can just go back to our master equation here for the time constant. We now know the equivalent resistance, equivalent capacitance. We can just plug them in. We've got R over 2 times C over 2, and that's just RC divided by 4, 2 times 2. And so by assembling two resistors, two capacitors in this particular arrangement, we've actually made a circuit that has a time constant that is 1/4 of the time constant of our circuit over here on the far left. Let's do the same thing for the third circuit, which is the one over here on the right-hand side. You might be guessing the answer to this one by now, but the same starting point applies, that the time constant for this circuit is the equivalent resistance of this network of resistors in the circuit multiplied by the equivalent capacitance of this network of capacitors in the circuit. And so our job is really, again, just to figure out what the equivalent resistances and equivalent capacitances are. In this case, our two resistors here are in series with one another. This makes a bigger resistance. The sum of resistors in series gives the equivalent resistance. In this case, with two identical equivalent resistances, the sum is going to be just R plus R, so 2R. That is the equivalent resistance. Now working downstairs to the two capacitors. We got two capacitors in parallel here. When you have two capacitors in parallel, again, you make a bigger capacitance, you make a larger capacitance. The equivalent capacitance for capacitors in parallel is the sum of the individual capacitances. So again, we got a relatively simple case. We just got a pair of capacitors and they're identical. So we just got to add these up. So it's going to be C plus C, that's the sum of the two capacitances. That's going to give us the equivalent capacitance, and that equivalent capacitance is going to be 2C. And so now we know the equivalent resistance, equivalent capacitance of the circuit. I can just plug them into my equation for the time constant. I'm going to plug in 2R for the equivalent resistance, 2C for the equivalent capacitance. I've got a time constant that is 4 RC. And so here are the three time constants of the three circuits, our reference point where we have one resistor, one capacitor. When we made this particular circuit here with the resistors in parallel and the capacitors in series, what we were effectively doing was in each case making a smaller resistance or a smaller capacitance that made a much smaller, by a factor of 4, time constant. We did the reverse in this circuit over here. When we combine the resistors in series and the capacitors in parallel, we made a bigger resistance and we made a bigger capacitance, and so we made a much bigger, by a factor of 4, time constant. Using the RC on the left-hand side as our reference point, it is faster to charge or discharge this circuit arrangement in the center by a factor of 4. Its time constant is smaller by a factor of 4 compared to the left-hand side reference time constant. For the right-hand circuit, this circuit will take 4 times more to charge or discharge the capacitors because its time constant is a factor of 4 larger than the reference circuit over here. There's two other circuits we might have drawn with our collection of identical resistors and identical capacitors that we haven't yet drawn in this problem. There's this one on the left-hand side where both the resistors and the capacitors are in parallel, and this one on the right-hand side where both the resistors and both the capacitors are in series with one another. So what would be the time constants of these? Let's just figure that out. This is for fun, right? For the parallel arrangement of the resistors and capacitors, the equivalent resistance of two resistors in parallel, well, that's a smaller resistance. If they're identical, it's just going to be R over 2. For the capacitors in parallel, that's actually a bigger capacitance, makes a bigger capacitance, more ability to store charge. Its capacitance will be 2 times C, the individual capacitors. So this circuit here has a time constant, which is half of R times 2 of C. The 2 in the numerator and denominator will cancel out. This is just RC. So it's identical to our reference circuit. Walking over here to the series circuit, we've got a pair of series resistors, a pair of series capacitors. There's 2 series resistors make a larger resistance. Because they're identical resistances, this will just be 2R. The 2 series capacitors, that makes a smaller capacitance, less capable of storing charge. This one is determined by adding the inverses of the capacitances to get the inverse of the equivalent capacitance. But simply because it's 2 identical capacitances, this is just a capacitance of C over 2. So again, when we come to calculate the time constant of this arrangement, we've got 2R times C over 2. The 2 in the numerator, 2 in the denominator cancel out. We've got a RC time constant that is, again, just RC, just the product of the individual values of the resistances of the capacitance. And again, it's the same as our reference circuit over here. Anyway, that was an example, an illustration of RC time constants for different circuit arrangements. It involved our understanding of capacitors in series and parallel and resistors in series and parallel. So it put together all that work we had done on resistor circuits, capacitor circuits, and charging, discharging of capacitors through resistors.